Hello, welcome. My name is John Morrow. I'm a professor of materials science and engineering at Penn State University. Specifically within the field of materials science, I am a glass scientist. This means that I study the fundamental physics and chemistry of the glassy state and apply that understanding toward the design of new glass compositions or understanding the relationships between glass chemistry, structure, and properties. Now, one of the most common questions that I get as a glass scientist is what is shown on this slide and the topic of today's presentation. Is glass a solid or a liquid? There are a lot of conflicted opinions on this amongst the general public and even among some scientists. And it's actually a rather subtle question. So I would like to spend this presentation to discuss whether glass qualifies as a solid or as a liquid or something else entirely. Here's a picture of some of my students pouring out some freshly melted glass from one of the furnaces in our lab. You can see as the molten glass comes out of the crucible, it is flowing like a solid. But as the glass forms at the bottom here, the viscosity is increasing rapidly, and this liquid, this molten state, is gradually converting into the glassy state. So it's gradually going from something that appears very much like a liquid to something that appears more like a solid. When this happens, this is called the glass transition. The glass transition is this continuous conversion between the molten state, the liquid state, and then the glassy state, which has mechanical properties that are more like a solid. Now, what are some of the words that are often associated with the glassy state? Some of those that we hear are vitreous, non-crystalline, supercooled liquid, and amorphous solid. These are words that people use in conjunction with the glassy state somehow. And what I'm going to show you today is that these first two terms are accurate. The word vitreous here is just a synonym for glassy. If something is a vitreous material, that by definition means that it is a glassy material. So vitreous and glassy by definition mean the same thing. So a glass is always vitreous. So we put a big green check mark next to that one. Glass, by definition, is also non-crystalline. It lacks the periodic crystal structure of most solid materials. In fact, the structure of a glass is frozen in from the liquid state. So the more disordered structure of the liquid, lacking in crystallinity, that's the structure that gets frozen into the glassy state. So all glass is non-crystalline. So these two words here, vitreous and non-crystalline, always apply to the glassy state. What about the next two terms here? The first one is supercooled liquid. Sometimes people define glass to be a supercooled liquid, and that is incorrect. Glass and supercooled liquid are two thermodynamically distinct phases of matter, as I will explain. And the next term here is amorphous solid. Many people also define glass to be an amorphous solid. And in fact, if you look at the Wikipedia page for glass, it even defines glass to be an amorphous solid. And that is also incorrect. And I will explain why during this presentation. And it's also the reason why you need to be careful when you're reading content on Wikipedia because it's not necessarily written by experts in the field. So the picture on the left shows glass. This is silica glass, SiO2. And on the right, this shows an amorphous solid, silicon, which is used in photovoltaics. You can see two of the applications here for glasses and amorphous solids. On the left, the glass here is being used in optical applications. And on the right, the amorphous solid is being used in photovoltaic applications. This glass on the left is silicon dioxide. It's vitreous silicon dioxide or vitreous silica because it is silica glass. On the right, this is an amorphous solid called amorphous silicon. Note that this is lacking any of the oxygen It is just amorphous silicon. And one of the themes of this presentation is that glass and amorphous solids are two thermodynamically distinct, non-overlapping phases of matter. A glass is not equal to an amorphous solid, and an amorphous solid is not equal to a glass. One of the main differences is that the structure of glass, such as vitreous silica, is frozen in from the structure of its corresponding liquid. So the structure of silica glass is very similar to the structure of silica liquid. Each silicon here is fourfold coordinated. It is bonded to four different oxygen atoms. Each oxygen is bonded to two silicons. And so the structure that the glass has is inherited from the liquid state. An amorphous solid, on the other hand, also has a non-crystalline structure, meaning that it is lacking the periodicity of crystals. However, the structure of an amorphous solid is different than that of the corresponding liquid. So amorphous silicon has fourfold coordinated silicon atoms that are all bonded to each other. But the corresponding liquid, so liquid silicon, is sixfold coordinated. So the structure of an amorphous solid is different from the structure of its corresponding liquid because the coordination numbers are different, the short range interactions are different, and therefore there's no connection between the amorphous solid state and the liquid state, whereas there's a very close connection between the glassy state and its corresponding liquid. What this also means is that the glass exhibits a glass transition because it is continuously connected to the liquid state, whereas an amorphous solid does not and cannot exhibit a glass transition. Now, how does this happen? Let's take a look at the plot here on the right. This is called the volume temperature diagram, and this explains how we get glass in the first place. So if we start off at high temperatures here in the liquid state around this point A, this would be the equilibrium liquid line at high temperatures. And if you cool the liquid from point A down to point B, the liquid would contract by an amount that corresponds to its thermal expansion coefficient. Now, if you take this liquid and you cool it just a little bit below its freezing point, then there is a thermodynamic driving force for the liquid to crystallize. This is a solidification process by which the disordered non-crystalline structure of the liquid, all those atoms will rearrange themselves into a perfectly ordered crystal structure. When that happens, there is a discontinuous change in all of our thermodynamic variables. So there's a discontinuous change in volume, as shown in this diagram. There's also a discontinuous change in enthalpy and in entropy, heat capacity, thermal expansion coefficient, and so on. And if this liquid, after it crystallizes, continues to cool, then it will follow this crystal cooling line going from point D down to point E, and the crystal will contract according to its thermal expansion coefficient. You'll note that this has a lower slope in the crystalline state compared to the liquid state. That indicates that the thermal expansion coefficient of the crystal is lower than that of the liquid. Now, crystallization is not something that happens instantaneously. Crystallization takes time because it takes time for the atoms and the liquid to move around and rearrange themselves into a crystalline lattice. What happens if you take a liquid and you cool it so fast through this gray region where crystallization is likely? You cool it so fast that you don't give the liquid enough time to crystallize. Then what we get is a phase called a supercooled liquid. A supercooled liquid is just a liquid that is cooled below its normal freezing point. The supercooled liquid is not a thermodynamic equilibrium phase. The equilibrium would be the crystal down here. Instead, the supercooled liquid is what we call a metastable equilibrium, meaning that if you leave it unperturbed, it will stay in its supercooled liquid phase for an indeterminate amount of time. However, if you perturb the supercooled liquid and give it enough thermal energy so that it can crystallize, at that point, it will undergo a first order thermodynamic phase transition. The supercooled liquid will crystallize into the solid state and achieve its true thermodynamic equilibrium. So the liquid is equilibrium at high temperatures above the melting point. Below the melting point, the crystal is in equilibrium. But if you take the liquid and you cool it so fast below the melting point that it doesn't have enough time to crystallize, then you will get a supercooled liquid. Now, if we take this supercooled liquid and we continue to cool it, what is happening is that the viscosity of the supercooled liquid is becoming higher and higher. And it's not just increasing by a little bit, it is increasing by orders of magnitude, meaning that the supercooled liquid is becoming less and less fluid. It's taking more and more time for the atoms in the supercooled liquid to flow, and they're getting a lot more sluggish in how they can move around. Now, at some point, the supercooled liquid becomes cooled to a low enough temperature where the kinetics that are associated with that viscous flow process become slow compared to the time scale on which you are observing them. So, for example, if you are looking at a supercooled liquid in the lab and pouring it out of a crucible, as the temperature is lowered, that viscosity is becoming orders and orders of magnitude higher. When that happens, the kinetics of the atoms are becoming slower and gradually they appear to freeze in, at least on our time scale of observation, whether that's minutes or hours or days or years. On a laboratory time scale or a human time scale, they are essentially frozen. This is not a thermodynamic transition. This is a kinetic transition. And this occurs because we are observing the system on a time scale that is shorter compared to the time scale that is required for the atoms to flow. This kinetic transition is a gradual process, and this is called the glass transformation, or more commonly, the glass transition. The glass transition is this gradual freezing in process by which the supercooled liquid slowly gets frozen into the glassy state because the kinetics of the viscous flow process become much too long to observe. And when that happens, we get the glassy state, this vitreous state known as glass, that has the structure of the supercooled liquid because the structure of the supercooled liquid was frozen into the glassy state. So the structure of a glass is akin to that of the liquid. But if you were to say bang the glass with a hammer or drop it, what you will see is that its mechanical response is a lot more like a solid. So a glassy material has certain properties that are like a solid, like its mechanical response. It has other properties that are like a liquid, such as its liquid-like structure. And it is continuously connected to the supercooled liquid through this glass transformation range or glass transition range. Now, is the glass equilibrium or even metastable equilibrium? No, it's not. Glass is a non-equilibrium state of matter that is continuously trying to relax back to its metastable equilibrium, which is the supercooled liquid. So the only reason that we observe glass at all is because we are catching it kind of frozen in time. We are observing it on a time scale that is too short for it to flow. But if you either wait a long enough period of time, or if you take a glass and you heat it up into this glass transition regime, then you're going to allow the atoms in the glass to flow and to go back to its metastable supercooled liquid phase. So the glass and the supercooled liquid are connected via this glass transition regime. And there is this continuous connection between the glass and the supercooled liquid, which is absent in the case of amorphous solids. Amorphous solids do not come from a supercooled liquid. They do not relax back towards the supercooled liquid, and their structure does not reflect that of the supercooled liquid at all. Those are the key differences between glasses and amorphous solids, that even though they're both non-crystalline materials, glasses are connected to the liquid state and amorphous solids are not. What's the difference between a glass and a supercooled liquid? A supercooled liquid is a metastable equilibrium state. A glass is a non-equilibrium state that you're not going to find anywhere in a phase diagram because phase diagrams only deal with equilibrium phases. And the only reason that we observe it is because it is kinetically frozen in. Now, one of the interesting things about glass being a kinetically frozen non-equilibrium material is that the properties of the glass, like molar volume, depend not just on the composition of the glass and the temperature and the pressure, but also the entire history of how the glass got to that point. So you'll notice here two curves, one for fast cooling and the other for slow cooling. If you take a supercooled liquid and you cool it really fast, then you're giving that supercooled liquid less time to stay in its metastable equilibrium. And as a result, the glass transition happens at a higher temperature range. And then the structure of this fast cooled glass reflects the structure of the supercooled liquid at a higher temperature. On the other hand, if you cool the supercooled liquid more slowly, you're giving the system more time to stay in its metastable equilibrium and only become kinetically frozen at a lower range of temperatures. Therefore, it would undergo the glass transition at lower temperatures, and then the frozen in structure of the slowly cooled glass would reflect that of a lower temperature supercooled liquid, whereas the structure of the fast cooled glass would reflect that of a higher temperature supercooled liquid. And one of the parameters then that we need to define for the glassy state that's kind of a stand-in for where it got frozen in from the supercooled liquid is called the fictive temperature, or T sub F. Here, we can get the fictive temperature by taking the glassy line here for the slow-cooled glass, intersecting it with the supercooled liquid line, and the point on the temperature axis where that intersects is called the fictive temperature. And that's not an exact description of the structure, but we can think of it as an approximation where the structure of the glass approximately corresponds to the structure of the supercooled liquid at that fictive temperature. So for the slowly cooled system, that has a lower fictive temperature compared to the faster cooled glass because the faster cooled glass fell out of equilibrium at higher temperatures since we gave it less time to stay in equilibrium. And therefore, its fictive temperature, which is labeled here as TF2, is higher compared to the fictive temperature of the slow cooled glass. So this is how we get glass, and this tells us kind of some of the key properties of glass. Now let's look at the definition of glass in the lower left part of the slide. Glass is a non-equilibrium, non-crystalline state of matter that appears solid on a short time scale, but continuously relaxes towards the liquid state. And I think we can make sense of this now, right? Glass is a non-equilibrium. It's non-equilibrium because it's not in thermodynamic equilibrium. It's non-crystalline because it is inheriting the non-periodic structure of the liquid state. State of matter that appears solid. It appears solid because we observe it on a time scale that is too fast for the atoms to respond in a liquid-like fashion. Therefore, it behaves mechanically like a solid. So it appears solid on this short time scale, but it continuously relaxes towards the liquid state because it is continuously connected to the liquid state. And the structure of glass, if we wait long enough, is continuously going to approach that of the supercooled liquid. So how is this different from amorphous solids? A glass continuously converts to a liquid either when heated or if you wait in the limit of long time. On the other hand, an amorphous solid does not and cannot exhibit a glass transition because the structure of an amorphous solid is very different from that of the liquid state. It follows that unlike gases, amorphous solids cannot be formed by quenching from a liquid. Most of the time, amorphous solids will form by vapor deposition processes, for example, where you've got an oversaturated vapor, and then the atoms are deposited onto a target. This is how you can build amorphous silicon, for example. One of the analogies that my advisor likes to give in explaining the differences between glasses and amorphous solids is what if you have like a chalkboard eraser here, and you could arrange the eraser in its lowest energy configuration by laying it flat on a table, because that's the lowest energy configuration that corresponds to the crystal. If you were to take this eraser and then tip it up on its side, this is a metastable configuration, because this is not the lowest energy. But if you leave this unperturbed, it's not going to fall over. However, if you perturb it, if you sort of knock it here on top, it could tip over and go to a lower energy configuration, which would be like the crystal. And the supercooled liquid is an example of this metastable configuration where let's suppose that you tip the eraser up, so it's standing upright like at a tower. This would be stable on its own if you don't perturb it, but if you kind of knock it a little bit, it could fall over and then go to a lower energy crystal configuration. The glass is unstable with respect to the supercooled liquid. So if you take this supercooled liquid and you tip it up on a corner, for example, glass is kind of like that because it's a non-equilibrium, unstable configuration that is continuously going to convert back to this supercooled liquid configuration, provided that you give it enough time to do so. So the glass is unstable with respect to the supercooled liquid, and the supercooled liquid is metastable with respect to the crystal. The amorphous solid is unstable with respect to the crystal, meaning that as an amorphous solid relaxes, it is not relaxing towards the supercooled liquid state, but rather it is relaxing towards the crystalline state. So it is a different type of disequilibrium compared to the glassy state itself. So to conclude this presentation, glass is defined as a non-equilibrium, non-crystalline state of matter. It appears solid on short timescales, but it continuously relaxes towards the liquid state. The glass transition is a continuous kinetic transition between the liquid and glassy states. A glass exhibits a glass transition, an amorphous solid does not. So to circle back to the question at the beginning of this talk, is glass a solid or a liquid? Yes, glass has certain properties that are liquid-like, and it has certain properties that are solid-like, but glass is its own unique phase of matter, that is combining features of both liquids and solids, and also bringing some of its own properties to the table too, by virtue of being a kinetically frozen non-equilibrium material. So glass is neither a true liquid nor a true solid. It is its own thing. And so if you want to learn more, please feel free to ask any questions down in the comments. Also check out our textbook, Fundamentals of Inorganic Glasses, which covers all of this and much more in great detail. Thanks everyone for watching, and hope you have a great rest of your day.